Do question 3.79, and basically I'm going to do part B, try C, and try for C. And so basically you have this wall that heats this inside chamber, and it has a uniform heat generated. And so basically for part B it's asking what are the temperatures at the wall boundaries for conditions of part A. And so for part A, what you need to know is that with that electrical strip, it's providing a uniform heat flux. So basically the temperature gradient at T0 will be 0. Alright, and so, and the other part is that since there's uniform energy being generated, that it's a parabolic shape. And so from that we can use equation 3.45, which you can see right there. Alright, and so our first step is to solve, solve for the boundary conditions, BC, boundary conditions. Alright, so as I previously noted, we know that the temperature gradient at the 0 condition must be equal to 0. Alright, so from that we can do at 0, you know what, oops, sorry. We'll do this. We're going to solve for the temperature gradient of that, which is Q dot 2K over 2x plus C1. Alright, and then once you, so at x equals 0, we're going to get we'll get the temperature gradient of dx will be 0 plus C1, and this must be equal to 0. So, which implies that C1 is equal to 0. Alright, solve for that. So our new equation becomes Q dot 2K x squared plus C2. Alright, and so we know that at T0, that must be T1, which will be Q dot 2K times 0 plus C2. Alright, and so this implies that C2 is equal to T1, because this right here becomes 0. Alright, so our new equation and final equation for solving for the boundary conditions becomes 2K plus T1. Alright, so now we need to solve for T1. And so if we go back up to my picture, I'm going to do an energy balance around this wall. Right here, that one that's highlighted. Alright, and so basically if we do E in minus E out, E generated must be equal to 0. Okay? So there's nothing going into it. Here, I probably should draw it out. There's energy being generated, which we're already taking into account for it. So we don't, that is going into it, but it's already in there. And then we have, it's already in the formula, so it's already taken into account. And then we have convection going out. So basically what we have is convection and the energy being generated. And so that's going to be at that minus T infinity inside plus Q dot L must equal 0. Okay? So we can rearrange this and get TL by itself. The reason we want TL is we can plug that into that new equation we found up there. So QL equals Q dot L dot over H plus T infinity N. Alright, so, and we know that at the length, that's one of the boundary conditions, so we know that's going to be equal to T2. Alright, So we can solve this for T2. T2 equals, alright, so it's going to be 1,000 watts per meter times, it's going to be 0.2 meters over 20 watts meter squared Kelvin plus, what's T infinity inside? 50 degrees C. 50 degrees C, and that will get you, let me see, alright, we'll get you 60-ish degrees C. Alright, so from there, we know that at TL, which equals T2, which equals 60 degrees C, and then we can solve for this, the new equation, which is Q dot 2K over L squared, because we're plugging in L for X, plus T1. Sorry, that's a minus right there. I don't know why. Did I forget it up here? I did. I forgot to bring that. And I forgot the X squared. Sorry, guys. Minus. Alright. So, from there, we can rearrange this and get 60 degrees C plus this Q dot over 2K, and there I go writing stuff wrong again. T1, which equals T1, okay? L squared, alright, everything looks good. Alright, so 60 degrees C plus 1,000 watts meter cubed times 0.2 meters squared over 2 times, what is the K value of the wall, which is 4 watts meter Kelvin. Okay, let me see. Four watts meter Kelvin. Okay, and so that will get you 65 degrees C. Alright, so T1 equals 65 degrees C, T2 equals 60 degrees C. Alright, and I'm not going to have enough time to be able to do part B, or part C, but it's not hard. I can help you guys set it up. So basically you have to determine the Q value. Actually, I'm not going to have enough time. I'll make another video.